Okay, welcome back. We have just found the general expression of the kinetic energy of a robot manipulator considered as a serial chain of rigid bodies. And the total kinetic energy can be written in this quadratic form with a positive definite symmetric inertia matrix multiplying in the quadratic form the joint velocity or generalized velocity in q dot. Now what is missing is a general expression for the potential energy. So this is computed quite in an easier way with respect to what we have done for the kinetic energy. The same property of addition of contribution holds, so the total potential energy will be the potential energy of each body. And again, if we are assuming that we have a serial chain, the potential energy is only a function of the configuration. And if we are computing the potential energy of a certain link I in the chain, this will depend only on the joint variable that precedes that link. So from J going from 1 to I. So the expression, the general expression for the potential energy is very simple. It needs to compute the height, in some sense, of the center of mass and its position with respect to the gravity acceleration vector g. So the expression for the potential energy of link I will be a minus, this is kind of a surprising term, but minus mass of the link I times the scalar product between the gravity acceleration vector g and the vector that goes from the origin of the reference frame to the center of mass of link I. Now, everything should be expressed. This is a scalar product of two different vectors, so they should be expressed in the same frame, typically in frame 0. For instance, if we have an elbow-type manipulator with the first joint axis revolute and vertical, so that the robot will move in this way, rotating around the first joint axis. So the zeta 0 axis will go up, and the acceleration gravity vector will go down along the zeta 0 direction. So you will have a g vector, which will be 0, 0, minus 9.81, which is the acceleration at the sea level. Okay? Indeed, if you're mounting this manipulator, let's say, on a wall, its zeta 0 axis, so the axis of the first joint, will be horizontal. And then, let's say that you choose x0 along the downward vertical, then the g vector will take a different expression. We'll have plus 9.81 in the x0 direction and then 0, 0. In fact, in this way, you can take into account for robots that can be mounted in any orientation of the base, so on the floor, on the ceiling, on a wall, on an inclined plane, this information can be coded into the software so that the actual acceleration of gravity and thus the contribution of the gravity term to the dynamics of the model can be adapted according to how you change base. So this is very important and very useful. Now, if you're using frame 0, then also the vector going from the origin of frame 0 to the center of mass of link I should be expressed in the same frame. Now, we said that this term is only configuration dependent. Again, we don't see explicitly a q here. So where does the q come from in this expression? Well, this is quite easily because we know that we can compute this vector starting from the vector, these are applied position vector, that goes from the origin of frame I to the center of mass of frame I, and the frame I is attached to link I, so this vector is constant and can be defined once for all for any rigid body. Again, I'm using my pointer. This is a rigid body. If my frame I is attached somewhere, let's say at the corner, in this frame I can characterize the position of the center of mass in a unique way, And in this frame, even if the body is changing its orientation and position in space, the vector RICI expressed in frame I will remain constant. And now, to transform a vector going from one origin to the center of mass into another origin to the center of mass and changing also its frame of representation, we need to use homogeneous coordinate and the homogeneous transformation matrices generic I-1I, which we have introduced in the Dynamic-Hartenberg convention. So you see that the kinematic part should not be forgotten. Once you set up the system, you will use it for kinematics, and you will use it later on now also for dynamics. So this, you border with a 1, this becomes a 4-dimensional vector, and then you express, after this product, this will be the homogeneous version of the vector going from the origin of frame I-1 to the center of mass of link I, expressed in frame I-1. And so on, you go back until you reach this, and this will be the vector, exactly the vector going from the origin of frame 0 to the center of mass of link I, expressed in frame 0. And if you're writing G in the same frame, this product, this scalar product, can be done. So the dependence on Q and the fact that in serial chain you have only a dependence on the Q up to the index of the link that you're considering, Q1 to Qi, when we are considering the position of the center of mass of link I, it's clear from this formula. Okay, so let's summarize what we have done. And the purpose of the following slides is to understand that there's a general dependence of the various elements of the dynamic model from position, velocity, and acceleration, and that we can also not apply, like we have done in the simple example of the actuated pendulum, the Euler-Lagrange equation, but we see the application in general, what will be the actual results in terms of dynamic terms. So my message, or the message that you should take home, is that once we look at this general structure, we will find a way in which to compute the individual element of the dynamic model in a direct way. Of course, based on the Euler-Lagrange system, but we will never build the Lagrangian and apply the equation as such. We apply the result of a processing of the expression of kinetic energy and potential energy in the model. So, for doing this, let's summarize things. So we have seen that the kinetic energy of the robot is a quadratic form in the generalized coordinate q, velocity q dot. So you can imagine the joint velocities. And there's a matrix, symmetric matrix and positive definite inside this quadratic term. Now, you could prefer to use the matrix vector format or to expand this into scalar contribution. And the scalar contribution is a double summation over the index I going from 1 to n, the number of links, and the index j going from 1 to n of the individual element of the inertia matrix, Mij, which are function of q in general, times the cross product between the joint velocity of joint I and of joint j. And of course, in this summation, the matrix is symmetric, so Mij will be equal to Mji. So this is the scalar version, and we will use the scalar version for the next derivation, but you can do the derivation also in vector matrix format. So this is our property. We know that this is very important. And the potential energy, we don't get any particular structure. We just have seen that is a function of Q. So we built the Lagrangian, and we should apply this equation. So we should look at the generalized coordinate qk and velocity qk dot, do the partial derivative. This derivative should be differentiated with respect to time. You do the subtraction. And on the right-hand side, we will have all non-conservative force, so both active and dissipative, that perform work on the coordinate qk, and k goes from 1 to n, and this boils down into a set of n second-order differential equations. But let's look in detail what happens when we do this derivation. So again, the expression of the Lagrangian. And let's do the individual derivation for the generic kth equation, with k going from 1 to n. So if you take the derivative with respect to q dot k in the first summation appears twice, when I is equal to k and when j is equal to k. So when you consider one of the two, let's say I or j equal to k, then you will have mi k q of q dot I times q dot k. So you take the derivative with respect to q dot k. So you have the summation with respect to the index I. And you do the same in the opposite situation. So you have twice the same summation because of the symmetry of the inertia matrix. So you can remember that this summation, when they saturate all values, so going from 1 to n, are also called mute summation. So you can call the index I, you can call the index j, you can call the index k. You can replace the index in any notation you wish. So the result is a summation over j from 1 to n of mkj, so the elements of rho k of the matrix M, the elements from 1 to n, each multiplied by the associated joint velocity. So the summation is over j. So now, of course, I've not written the dependence of this element from Q, but this is implicit, just to simplify notation. So this is one contribution. Of course, the potential energy does not contribute to this term because potential energy does not depend on velocities. Now, we have to take the time derivative of this quantity. This is what the generic equation in the Euler-Lagrange form required. So the derivative of this, of course, on each terms in the summation, we have the derivative of the velocity, which generates the acceleration. So we have a summation of mkj times q double dot of j. And then we have to take the time derivative of the elements mkj. So they are function of time through the fact that q is a function of time. So we do the partial derivative of the generic element mkj in this summation with respect to every possible dependence on q, so on q1, q2, qi to qn. So we have, again, a new summation over the index I, and every time we take the derivative with respect to qi, then we have to take the derivative of qi with respect to time, and so we have the product by qi dot. So this is the full expression. And you see that while doing the derivative, we keep still the elements of the inertia matrix, but we also introduce partial derivative of the element of the inertia matrix with respect to the generalized coordinate. Indeed, if the inertia matrix were constant, this partial derivative will be 0, and this is a very important property. Now, the other part in the Euler-Lagrange equation is the partial derivative with respect to the generalized coordinate k. So if we look at the kinetic energy part, the q dot remains as such. The dependence on the individual k is within the elements mij. So we have to sum, for each mij, we take the partial derivative with respect to qk, and then we sum over I and j, like in the previous expression. While here we have also a contribution coming from the potential energy. So the minus sign is because the minus is present in the Lagrangian. And then we have a partial derivative of u with respect to qk. Now remember that u, L, and every element are scalars. So this is again a scalar, this is a scalar, and so on. This is why this type of notation is a scalar notation with summation instead of using the vector matrix form. Now, so this is everything you need because the Euler-Lagrange equation will be this term minus this term equal uk, the non-conservative forces doing work on qk, and k goes from 1 to n, all the generalized coordinate. So if you look at the individual term, you will see that the model, so the left-hand side of our Euler-Lagrange equation, will always be linear in the joint acceleration. The acceleration appears only here, pre-multiplied by elements of the inertia matrix. In fact, in the kth equation, by the kth row of the inertia matrix M of Q. So the model will be linear in the acceleration Q double dot. Similarly, the velocities appear both in this term, in this summation, and in this summation. And every time they appear with a product between the same joint velocity or different joint velocities. In any case, there will be only quadratic term coming from the Lagrangian in the velocity. So the model will be quadratic in the velocities Q dot. Pay attention. There may be other terms which are linear in Q dot, but they are coming from dissipative terms. So they are on the right-hand side of the equation. This is what we have seen for the actuated pendulum when we have considered some dissipation due to viscous friction on the motor side and on the link side. They were linear terms in the velocity, but they were not coming from the Lagrangian. All terms that come from the Lagrangian, so from kinetic energy in particular, will be quadratic in the velocities, in the dynamic model. And finally, all the rest is nonlinear in terms of the configuration. Remember, we skipped the dependence, but the elements of the matrix M are function of Q, so this is a function of Q. Their derivative continues to be function of Q, and also the potential energy is a function of Q. Its derivative with respect to Qk is still, in general, a function of Q. And these dependence are nonlinear, typically trigonometric dependence on the Q. So these are structural properties that are always present. Another structural properties that we have seen is that the inertia matrix M of Q, which appears in the quadratic form, which expresses the total kinetic energy of the manipulator, is a positive definite matrix, no matter which configuration the robot has. And this is, of course, a physical property coming from the fact that we are expressing a non-negative quantity like the kinetic energy is. So now let's put this all together. So we are writing the left-hand side, and we have the linear terms in the acceleration, the quadratic terms in the velocity. They are coming from two sources, and then the nonlinear terms coming from the gradient of, or the derivative of the potential energy. Now we can massage a little bit this generic equation. This is the kth equation out of n. In particular, look at the following. If you're taking this element, so this is rho k column j in the inertia matrix, and you're taking the partial derivative with respect to another generic coordinate. Now, this element, if you take the elements where you exchange I and j, pay attention, not k and j, because if you exchange k and j, you obtain the symmetric element in the inertia matrix, which will be the same. So this partial derivative will be the same. So stated differently, mkj, partial derivative of mkj over qi is equal to partial derivative of mjk over qi. But if you're taking now, this index are mute, so if you're now exchanging I and j, so you're considering this partial derivative and the partial derivative of the ith element of the rho k with respect to the j variable, this in general will be different. And this in scalar terms seems irrelevant, but in matrix term, this will lead to a non-symmetry of this contribution. So the next step that we do is really symmetrizing this situation. So we take into account this part, and we do twice the summation by exchanging the mute index. Okay? Now you see that we have the result will be the same because we sum over all indices. So we have one term and the other term where we have exchanged I and j. Since we do this, we complete the summation. This will be the result will be exactly the same. So we are doing twice the same summation. So we introduce a factor 1/2. Also, this term had the factor 1/2, so the factor 1/2 can be factorized outside. And all the rest remains the same. So this is just to show that we have introduced with this term what are called in mechanics the Christoffel symbol associated to the inertia matrix. These are all terms that are computed through partial derivatives of the elements of the inertia matrix with respect to the coordinates. And you see Qi, Qj, Qk, and this is the kth equation, so kth remain fixed, but all the I and j are summed over the all indices from 1 to n. And because of this, this coefficient, when you exchange I and j, you find full symmetry, so you find the same terms. Now, these Christoffel symbols, why are they relevant? Because they are exactly the contribution, the weighting to the quadratic terms in the dynamic model, the quadratic terms in the velocity. So these are very relevant. Of course, if the matrix, as a special case, would be constant, all this partial derivative would be 0, so there will be no dependence on quadratic velocity in the model. This is an automatic consequence of this structure. Okay, so now let's rewrite those terms once we have symmetrized things with the Christoffel symbols. See, we have the m elements, mkj of the inertia matrix. We have the Christoffel symbols which are weighting the quadratic velocities in the model, and then we have a gravity-related term. Now we give an interpretation of each of these terms. So these are the inertial terms. In fact, they are multiplying the acceleration. These are the multi-body version of something that says F equal m times acceleration. The m is not a scalar mass. It's the combination of inertial properties of several rigid bodies depending on their configuration. So in any case, they are inertial terms. These instead are the so-called centrifugal and Coriolis terms. In particular, when the index I, this is the kth equation, remember, so k remains fixed. The index I and j are summed over all the index from 1 to n. So when in the summation you have that I is equal to j, so you will have a Coriolis, Christoffel symbol of the form CKII, then you have the product of Qi dot times itself, so you have a quadratic terms in Qi dot, and this is a typical centrifugal contribution. Instead, when you have two velocities appearing, so when I is different from j, you have some dynamic terms in the model that depends on this cross velocity. So there are torques that are felt by the different links because two links are moving at the same time. You may remember from basic physics course that a typical Coriolis effect is when you have, let's say, a boat moving in the ocean from, let's say, from the equator to the north, while the Earth is rotating, and this gives this coupling of its linear velocity of the boat and the angular velocity of the Earth, which generates a linear velocity sideways. This will generate a force which will tend to rotate the boat in its way. So this is called Coriolis effect. And in fact, the fact that you have a multi-link body connected and with simultaneous velocity of different bodies will generate also this quadratic in the velocity terms, but with the product of different velocities, not the same one. And finally, the last term is very easy, is the gravity term. It's just a component of the gradient of the potential energy with respect to the q vector. Each component is a partial derivative with respect to a generic component qk. So now, what are the terms that appear here. So if you look, for instance, at a diagonal element in the inertia matrix of our robot, so mkk in equation k, then this will be the inertia that will contribute from the whole structure on joint K when you have that only joint K is accelerating. So suppose that you're working on the horizontal plane, so the potential energy is constant, so the gradient is 0, and you're starting at rest, so all velocity are 0, so all the blocks in red are 0. So what remains is only the left-hand side, the inertial terms. Suppose that all acceleration are 0 except the kth one. So you have really an equation uk equal mkk times q double dot of qk, which is the generalized form of F equal m times a. So the mkk in the configuration q, so this is a function of the configuration in general, will be the actual inertia seen when you're accelerating only the kth joint, okay? And because of the positive definiteness of the inertia matrix, its diagonal element should always be positive for any configuration Q. So you see that the acceleration will have the same sign of the applied torque at the joint. Similarly, an off-diagonal element of the inertia matrix reveals that there's an inertial coupling between the acceleration of one joint and the acceleration of a different joint. So if mkj is different from 0, and in the current configuration, so this is in general also a function of the internal configuration of the arm, then this element will be the inertia seen from joint K when joint J is accelerating. So there's a coupling inertial effect, and this coupling is expressed by the presence of this element. And similarly, if we look at the Christoffel symbol, so at this scalar coefficient, which have 3 index, pay attention. One index refers to the equation that we are considering, K, and then I and J refers to the product of velocity, either the same velocity when we have II or different velocity. So this is the coefficient that weights the centrifugal force felt at joint K when joint I is moving. And similarly, the CKIJ will be the Coriolis force felt at joint K, because we are looking at the kth equation, when joint velocity I and joint velocity J are different from 0. So Qi dot, Qj dot is different from 0. The effect of the force on joint K is modulated by this coefficient. So each term in the model can be given a physical interpretation. So when you put everything together, you end up with the following form. And now I'm resuming a vector format. Okay? So let's go back. If you're looking at one equation, the first term, for instance, the inertial term, will be for rho k in the set of equation, will be the sum of mk1 times the acceleration 1, mk2 times the acceleration of joint 2, and so on. So in fact, it will be the complete kth row of matrix M multiplying the full vector Q double dot. If you stack the n equation from k going to 1 to n, you will end up with the first part. So the inertia matrix times the acceleration vector. Now, all quadratic terms in the velocity are collected into a vector, which is a function of q, like all the terms, and of q dot, and we know already that this vector will be quadratic in q dot. You see that this is a structural property, and we know that they depend, the dependence on q will be a function of how the elements of the matrix M depends on q itself. And finally, the last term, the gradient of the potential u with respect to q, will be a column vector. Remember, the gradient is a column, is a row, but we transpose it, so we have a column vector. And on the right-hand side, we have all the non-conservative forces. Now, we can give an explicit form for C. We know that it's, in fact, a quadratic in Q, so it's a quadratic form. The generic element, Ck, of this vector C will use the Christoffel symbol, which have the first index equal to K. And in fact, you can organize all this by changing I and j in their element as a quadratic form in the velocity, where inside you have a matrix which is exactly computed by those partial derivatives of the element of the inertia matrix with respect to the q coordinates or the qk coordinates in particular. So this is very convenient because you can automatize this computation. We will show an example with a Matlab code in a systematic way. What are MK? MK are the column, MK is the kth column of the inertia matrix. So this symmetric matrix that you put inside this quadratic form, which generates the kth component of that vector, will be computed in this way. You take the kth column of the inertia and you take the partial derivative with respect to q. This, in general, is a non-symmetric matrix, but in fact, we have seen in the scalar version of this that you can add the transpose and then divide it by 2, and then you symmetrize this part. And then you have to subtract, this is the other contribution coming in the Christoffel symbol, you take the derivative of the whole matrix with respect to the scalar qk. Okay? So mk is a column. The partial derivative with respect to q makes this a matrix, non-symmetric. You add the transpose to symmetrize, and then you divide by 2. The factor 1 over 2 was present also here. Matrix M is symmetric. Its partial derivative with respect to the scalar qk is, again, a symmetric matrix, and you subtract this to this expression. And all this will be the leading matrix, a function only of q, pay attention, because the dependence on q dot is factorized out in this quadratic form. Now, this is a very convenient way of organizing computation. And I would say that once you have computed the kinetic energy, and this is the trick, now you forget completely about the Euler-Lagrange equation. You compute the kinetic energy, you realize that this kinetic energy is a quadratic form in the velocity, you extract from this scalar the inertia matrix, which is the matrix multiplying the quadratic terms in the velocity, and you have m of q. Full stop. You have already built one of the elements of your dynamic model. And the next step is you take this matrix, you take the column of this matrix, of the matrix as such, you make these partial derivatives, and you compute this n by n matrices, which for each joint contribute to joint 1, joint 2, joint n, so for k going from 1 to n, and in the quadratic form generates the components of the vector c, which is the Coriolis and centrifugal vector in the model. So again, from the kinetic energy, you extract the inertia matrix, you do this partial derivative, and you have the first two parts of the model. The last part is very easy. You compute the total potential energy, you make the gradient, and you obtain the g of q. Now, we will see that the C vector sometimes is useful to factorize this, knowing its dependence on q dot, in this way. So you take out one of the quadratic terms of q dot, here linear, and then what remains is a matrix S, which will be nonlinear function on q, but a linear function on q dot, so that you recover the quadratic dependence. So this factorization is not unique in general. So in general, this factorization with this S matrix, so the factorization of the Coriolis and centrifugal term, will be given by a matrix which is not symmetric in general. However, there's a way of computing the element of this factorization using the Christoffel symbol, which will introduce a nice control properties between the M matrix and this S. And we will see that this structural properties, which holds for any robot, once you factorize in this special way, among the many ways, the Coriolis and centrifugal term, will satisfy some property which enables us to make some nice conclusion on the characteristic of some controllers of the robot motion. So this is a very strong property. It's a skew symmetric. In fact, I anticipate this. Skew symmetry of the time derivative of m minus twice this matrix. This is a skew symmetric matrix, and this property will be used later on. Okay, so now see, whatever format, so this is the generic one, this is including a factorization of the Coriolis centrifugal terms. Whatever form you're using, you see that we ended up with finding what we were looking for. When we started last time introducing the generic model, we said we will end up with a set of n differential equations that depends of the second order type, because they depend on q, q dot, and q double dot, where q are the generalized coordinates. And on the left-hand side, we will have the non-conservative forces. And here is exactly how this generic dependence function, phi of q, q dot, and q double dot, how it is structured internally for any robot. No matter how many joints there are, no matter how the links are made, heavy, light, uniform mass, strange couplings, prismatic joints, revolute joints, all the robot models will have this structural form, which we derived in symbolic terms using the Euler-Lagrange approach, which is an energy-based method. And this is the advantage of this situation. So let's do a first significant example. We have already done this, but more through intuition with the actuated pendulum. Let's do the same following the steps that are suggested by the Euler-Lagrangian approach, so computing the kinetic energy, extracting the inertia matrix, doing some computation, partial derivative on the elements of the inertia matrix to generate the velocity term in the model, which are quadratic, and then compute the potential energy, extract the gradient, and complete the modeling stage. So the most simple case that I could think of for doing this computation is this 2 degrees of freedom robot, which is a planar robot with the first joint being prismatic and the second joint being revolute. And all the motion lies in a plane. Now, it's really important to understand if this plane is horizontal or vertical. While from the kinematic point of view, this is completely irrelevant. Here, if it's vertical, then the motion of this arm will be subject to gravity. If it's horizontal, gravity is there, but gravity will not perform any work on the coordinate. So, in fact, it will be constant. So we can compute the potential energy, but this potential energy will be constant no matter which is the configuration of the arm. So its gradient with respect to q will be 0. So this term vanishes. Instead, if we are in the gravity field, so with a vertical plane or an inclined plane which feels a bit of gravity acceleration, then we need to compute the potential energy and its gradient. So here we assume that we are, despite the slide is vertical, we assume that this is a horizontal plane. So u will be constant and the gradient will be identically 0. So the gq term will vanish in the model. So we will end up with a model which has m of q, q double dot, plus c of q, q dot equal the generalized non-conservative forces acting on the q's. And since the robot has 2 degrees of freedom, we will have 2 such second-order differential equations. So let's introduce some quantities. Let's call PC1 the position in frame xy, which is an absolute frame, of the center of mass of the first link, which translates the position of the first joint is characterized by the variable q1 from the axis y, and q2 will be the angle of the second link with respect to the x-axis, and pc2 will be the position of the center of mass of the second link. Now, the center of masses are constant in the link, the position are constant, but of course their position with respect to the absolute frame xy will change while q1 and q2 are changing. So let's call dc2 the distance of the center of mass of the second link from the joint axis 2, and we'll see that this is convenient. Let's call dc1 the distance between the center of mass and the position of the joint 2. Of course, the center of mass will move according to q1 and will be just offsetted by the constant dc1 with respect to the position of the joint axis 2. Now, one warning here, that x and y are not x0 and y0 of a Dennavit-Hartenberg notation. Because in this case, since zeta 0, the only thing that is being fixed should be along the first joint axis, and the first joint axis is this prismatic one, so this should be the zeta 0 axis, while here I've labeled it as x, because we are on a plane, so it's natural to consider the two coordinates x and y. And similarly, q2 may not be the Dennavit-Hartenberg variable theta in this case, but it's very convenient because with q2 we characterize very easily the position of the center of mass 2, and therefore we can compute its velocity. Okay? So these are two generalized coordinates that we choose. They are very convenient for computing the quantity that we need. In our case, only the kinetic energy of the two links. So if we embed this in a three-dimensional space, though this is a planar situation, so we could restrict ourselves to the plane, but let's do the computation in the 3D space. So the position of the center of mass of the first link is along the x-axis, the absolute x-axis, and is characterized by the position of the joint 2, q1, minus this constant term, dc1. And then 0, 0, because there's nothing along y, there's nothing out of plane. Why do we compute PC1? Because we take the derivative, the time derivative of PC1, and we compute VC1, which is part of the kinetic energy of link 1. In fact, it's related to its translational part. So if we take the derivative of PC1, we get VC1, and we get just Q1 dot 0, 0, because DC1 is a constant. And if we take the norm of this vector and we square it, because we are in fact computing the scalar product of VC1 by itself, we end up with just the scalar Q1 dot square. So the kinetic energy of the first link, since the first link does not rotate, omega of the first link will be 0, so we don't need to compute anything, no inertia is relevant. The only term which is relevant is the first contribution in the Koenig theorem, so the kinetic energy due to the translatory motion of link 1, so 1/2 m1 VC1 norm square, so VC1 transpose times VC1. So this is very easy. It's just a mass. The fact that it's distributed on a link is not relevant because this mass, this link only translates along the joint axis. So the kinetic energy is just this one. A very simple computation. A bit more complex is the computation of the kinetic energy of link 2 because the link 2 translates while moving the first link, and the center of mass has also linear velocity because we are rotating the joint axis 2, but we have also an angular contribution, and this is due only to the rotation of joint 2. So in general, we should write both VC2 and omega 2. For writing VC2, we start again writing the position of the center of mass in the coordinate x, y, z, so 0 because everything is on the plane. So the coordinate x of the position of the center of mass of link 2 is q1 from here to the base of the second link, and then dc2 times cosine of q2, so the projection along the x-axis. Similarly, on the y-axis, you have only the projection dc2 sine of q2. And this is the expression of the position. Its velocity is the derivative of this. So you have q1 dot, and then the derivative with respect to time of this, it's minus dc2 sine of q2 times the derivative of q2 with respect to time, so times q2 dot. And similarly here, you have only q2 appearing, so the time derivative is just dc2 cosine of q2 times q2 dot. So this is the vector. You should take the norm of this vector and square. And now you have to take the square of this, plus the square of this, plus the double product of this, plus the square of this, and then possibly simplify things. And this will go here. While for the angular velocity of this body is on the plane. Its only rotational velocity is a vector around normal to the plane of motion. And its intensity is exactly the intensity of the joint velocity 2. So the vector omega 2 is 0, 0, q2 dot, which means that if you put this into this quadratic form, and you have a 3 by 3 inertia matrix of the second link, you're only interested in one component of this 3 by 3 matrix. No matter if this matrix is or diagonal or not, you're only looking at the ZZ component, so the element 3, 3 in this inertia matrix, because you're singling it out by this product. So 0, 0, q2 dot, 0, 0, q2 dot for the transpose, so you're taking only the element 3, 3 in this matrix. So if you put these things together, you take the square norm of this vector, you see you get the square of this term, then you have the square of this term, which is dc2 sine square q2 dot square, but then you have the square of this term, which has cosine square, so sine square and cosine square simplify, so you get, as a result, dc2 square times q dot square, plus the double product in this quadratic term, so you have twice dc2 sine of q2 product of q1 dot, q2 dot. Okay? And the second contribution here is q2 dot square, when you're doing this product, multiplying the element zz, so the last element on row 3, column 3 of the inertia matrix of the second link. So what matters is only the rotation of the last link. Pay attention, this is around its center of mass, so around the position PC2. And that's this contribution. This is because of the decomposition in the Koenig theorem. However, you can already realize that this part will be is only the kinetic energy of the first link. When you're computing the kinetic energy of the second link, you will see that the quadratic velocity here, so the actual rotation speed times square of the second joint, will appear multiplying the inertia around the center of mass of the second link plus m2 dc2 square, which is exactly the parallel axis theorem. So you're moving the inertia from the center of mass to the joint axis, so you have to add the mass of the second link times the distance of the center of mass from the joint axis squared. So this is automatically computed by the method. You don't need to apply. Once you realize that here, in this expression, you have to use the barycentral inertia. And then the conversion is automatically done by the equation. So this is the total kinetic energy of the second link. You add it to the first link, and you recognize that the total kinetic energy is a quadratic function in q dot. In fact, it has a quadratic function in q1 dot here and here, okay? M1 there and M2 here, plus it has a quadratic terms in q dot square here and here, plus has a cross product of q1 dot, q2 dot. So if I'm factoring out from this quadratic form the element that multiplies q1 dot square, the element that multiplies q dot square, and the element that multiplies q1 dot, q2 dot, and distribute this into the product of q1 dot, q2 dot, and q2 dot, q1 dot, we are exactly extracting the 4 element of the symmetric matrix of the inertia of the robot. So the result is the one on top. So by building up the total kinetic energy, we can immediately extract the inertia matrix, which is the inertial part multiplying the acceleration in the dynamic model. So without applying any longer the Euler-Lagrange equation from scratch, we already know the result. So we have this inertia matrix. You can see that the diagonal elements are constant, but the off-diagonal element, there was a factor 2, which has been distributed between the 2 elements M12 and M21, so that you have a symmetric matrix in the quadratic form. You can always do this. Now, we need to compute from there the Coriolis and centrifugal term. So the vector C of quadratic term in the velocity, where, as we have seen, each component of this vector, so ck for k1, 2, is a quadratic form in the velocity, and the inner matrix is a ck function only of the configuration, is obtained from the Christoffel symbol, so from partial derivative of the element of the inertia matrix, which is on top. For the kth matrix, for k going from 1 to 2, we use the kth column mk of the matrix and the total matrix. So let's call the first column m1 and the second column m2, and let's compute ck for k equal 1 or 2. So the first one, for k equal 1, this first partial derivative, so we have a factor 1 over 2, then we take the first column and we make the derivative of this column with respect to the whole vector q, so q1 and q2. This will give rise to a matrix, so we take the derivative of the first element of the column with respect to q1 and q2, and this will make the first row, but the first element is constant, so the first row will be 0. The partial derivative with respect to the first element of the column 1, m1, is 0, and with respect to q2 is 0. The second element, if we take the partial derivative with respect to q1, is 0. In fact, q1 does not appear there. And if we take the partial derivative with respect to q2, we will have minus m2 dc2 sine of q2. And this is the first matrix in this expression. Now, you see that this is already symmetric, but the rule, it may not be in general, the rule is to take the symmetric, the transpose of this and to add it. So we are adding again the same matrix because this is symmetric itself. And then we need to subtract the partial derivative of the whole matrix M with respect to Q1. But Q1 is not present in this inertia. So this matrix is identically 0. So we end up with twice this element on the position 2, 2 of the matrix. We divide it by 1/4, by 1/2, so we have this single element multiplying in the quadratic term, again, only the square of the velocity of joint 2. So the first component of the Coriolis centrifugal vector is in fact a pure centrifugal term with a minus sign. So this is the centrifugal force that link 1, the prismatic, which moves with the prismatic joint, feels when the second joint is rotating at the speed q dot. Okay, so it's the square of the speed multiplied by cosine of q2, and then with a minus sign. What about the second component of the Coriolis centrifugal term, so the c2 of q dot? Again, will be a quadratic form in the velocity with an inner matrix C2 of Q, which is now computed according to the formula by considering the second column of the matrix and making the derivative with respect to Q. Again, the first contribution, the partial derivative with respect to Q1 is 0. The partial derivative of the first element of the column 2 of the matrix M is minus M2 dC2 cosine of Q2. The second element of this column is constant, So its partial derivative with respect to Q1 and Q2 is equal to 0. And you see that this is a non-symmetric matrix. This is why, in general, we add its transpose to symmetrize the quadratic form. So we add to this its transpose, so we have the element here moving to the bottom part of the matrix. And then we have to subtract from the total derivative of the total matrix M with respect to Q2 now. So to Qk, and k is equal to 2. So we have a 0 here, because that term is constant, a 0 here. And the partial derivative of the off-diagonal term is minus M2 dC2 cosine Q2, and the same to the other side, because the matrix is symmetric. And we have to subtract this matrix. Now, all this computation is completely useless in a sense, because we are subtracting this element with this, and this element with this. So the final result is a 0 matrix. And being the 0 matrix factoring the quadratic velocities, the second term in this C vector will be identically 0. So there will be no effect due to the velocities on the second link. There will be only a pure inertial effect due to the acceleration. Now let's put everything together, and we end up with the model in the general form, now specialized to this case. There's no g of q because gravity is absent. We are considering the case in a horizontal plane. So the first part was immediately extracted from the kinetic energy. So the inertia matrix is the one that we have seen, multiplying the acceleration. And then from the C vector, only the first component is non-zero, and what is present there is a purely quadratic term of the second velocity. And on the right-hand side, we will put non-conservative terms. Now, it is very interesting now to make a number of observations on this model, which is the first multidimensional model that we are deriving with the Euler-Lagrange approach. And first comment, note that the last element, so in general, the nn element on the diagonal of the inertia matrix is always constant. Why? Because this is in fact the inertia seen when you're moving the last joint. You're accelerating the last joint only, all the rest is kept fixed. So this is like being a single link which is rotating around this joint axis. So this is the total inertia, it's constant. This property which holds here is true for any robot with any number of joints of any kind. So the last element on the diagonal is always constant, and here is a special case. Now, another thing that you should note, and this was used in the computation, is that the inertia matrix is not a function of the first coordinate q1, only of the second coordinate q2. This is a general property. If you take a robot with 7 joints, so with a q which is 7-dimensional, let's say the inertia matrix of the full KUKA lightweight arm that we have in the lab, then not only the element M77 will be constant, but in no element you will have a dependence on q1. Why is that? If you reason, and in particular, if you consider that in general we introduce the coordinate, if possible, using the Denavit-Tartenberg notation, you know what is the q1 variable in that notation, and it's related if the joint is revolute to the θ1 variable in the Denavit-Tartenberg notation, if the first joint is prismatic to the d1 variable, and those variables are defined with respect to a frame, the zero frame, which is somewhat arbitrary. If you think about this variable can in fact assume any value depending on how you choose frame 0. And this is why a physically intrinsic property like the inertia of the structure cannot depend on this variable. Because you would have larger inertia or a smaller inertia in an intuitive sense, depending on how you choose the base frame. And this is not physically consistent. So we said that when a variable does not appear in the kinetic energy, so in the inertia matrix, that this variable is a cyclic variable for the system. So Q1 will always be a cyclic variable. Pay attention. Q1 does not appear in the inertia matrix, but Q1 dot is important for the kinetic energy of the structure. So the fact that the inertia matrix is not depending on Q1 does not mean that velocity of Q1 is not relevant, okay? So this is it's an answer to this question. I will leave the other question open, but let's go through all of them. So why we end up with quadratic terms in the velocity only of the centrifugal type? Why there are no Coriolis terms, so no products of Q1 dot, Q2 dot? And this is a reason, please think about, and then we may discuss it separately or through our, let's say, conversation on the web. Another property is that you see that the centrifugal effect on joint 1 is only due to the fact that joint 2 is rotating. In general, you will never have on joint I in a serial manipulator a centrifugal effect due to its own velocity, only of velocity of the other joints. So, to state it in terms of a Christoffel symbol, we have a strong property that Cii is always 0. So, the contribution that the square velocity of joint I, so Qi dot square, has on joint I is always 0. So here you will, if you find here Q1 dot square, you have made a mistake in the computation. Okay? Here you don't have any centrifugal effect on joint 2 due to the motion of joint 1. In the same way that you don't have Coriolis terms, neither in joint 1 nor in joint 2. And you can reason about this. Third question. Now we have this equation. We can use this equation for doing direct dynamics. So we apply here some generalized forces. Remember that U1 is associated to joint 1, which is a linear, it's a prismatic joint, so it's a force, it's a linear force that you apply through the motors at joint 1. If you neglect all non-conservative forces, let's say all dissipative forces and other external forces, so only the motor torques. So this becomes a force on joint 1, and U2 is a torque because joint 2 is a revolute, so it's the torque produced by the motor once reflected after the reduction element or transmission element that you may have. We don't go into detail as we did for the actuated pendulum, but the same applies. So if you're interested in direct dynamics, you should ask yourself, what happened if I'm in a certain state, in a certain configuration with some initial velocity, for instance, 0 velocity, so that this goes to 0, and I'm applying no torque to joint 2, so U2 is 0, but I'm applying a force at joint 1. Then my question, will the first joint accelerate? Will the second joint accelerate? In which direction? Always, it depends, and so on. So I invite you to think about this by looking at the equation and how do they specialize and what will happen in this various situation. So imagine that there is no velocity at time 0, and at time 0 you're applying a positive force u1, no torque u2, what happens to q1 double dot and q2 double dot? Will they accelerate? Will they not? Will they accelerate in the same direction of the applied force or not? Another exercise that you can do, you can take the quadratic term in the velocity, so the vector c, and do a factorization. So extract one velocity vector, q dot, and keep the second velocity contribution into a matrix S. In this case, the factorization is very simple. Why? Because you have only this term here. So you can decide to factor out only q2 dot. There's no q1 dot to factor out. So q2 dot will go outside. What remains inside is just q2 dot. So the factorization will be 0, 0 on the second row, and just 0 and minus m dc2 cosine q2, q2 dot, multiplying the vector q dot outside. Okay, there's no other way of, and in fact, this is the way in which the use of the Christoffel symbol will generate this type of factorization. But indeed, I invite you to find that this is not unique. Even in this case, you can imagine to factor out some imaginary term that are not there, but they will cancel out in the factorization, so that you can make the statement, the factorization is not unique. And there are factorization that will not induce some strong, nice property to the matrix which is obtained by taking m dot and minus 2 times this S factorization. And we will see this more in detail later on. The last question is the most intriguing one. We have mentioned that, for instance, at the kinematic level, we have a manipulability index for a robot, which corresponds to the fact that in a certain configuration, we have a better transformation of joint velocity into end effector velocity. And of course, if we have redundancy for a given position of the end effector, we may find the best configuration that maximize manipulability, or maximize manipulability in a certain direction. Are there similar concepts at the dynamic level? So can we look at this inertia matrix of the robot and say, is there a configuration with maximum inertia? Remember, inertia is a matrix, so we should extract some information to understand that, in fact, there are configurations where the transformation between torques and acceleration is more favorable or less favorable, especially in certain direction. So I invite you to think about how can we define a scalar which is associated to this measurement of large or small inertia. It's not immediately evident. Now, I would like to do the following 2 things to conclude the lecture. The first thing is to address some, this question is related, the third one is related to the direct dynamics. I would like to do some inverse dynamics computation on this model. So you have the model on the screen. So let's consider a couple of examples of inverse dynamics for the PR planar robot. So the one that you have on the screen. Let's cancel this. So let's consider first this case. So what do we mean by that? We have already seen this problem for the actuated pendulum in particular. Now, assume that we give some desired motion. So some evolution for Q1 and Q2, and then we need to compute the torque that will, or the generalized forces, U1 and U2, that will produce that type of motion. So suppose that we are in this situation. So the Q1 desired of t is just the constant. So the first link does not move and is placed in some specific position, which means that Q1 dot desired, Q1 double dot desired are both equal 0. Okay? And for the second joint, we have an evolution like this. Alpha, and alpha may be positive, times t, which means that Q2 dot desired is equal to alpha, and Q double dot to desired is equal to 0. Now, the other thing is that from this expression is that Q dot 0 is, of course, k, and Q2 desired at time 0 will be 0. So we have an initial configuration, and so we can imagine that the situation is as follows. So we have the first prismatic joint, the first link is somewhere, so this value Q1 is constant, and the second link is in the 0 configuration, so it's aligned with this, the center of mass will be somewhere here, but has some initial velocity alpha going up, is here. Okay? Now, we are in a particular state and we are trying to execute this type of motion. The motion is very simple. Keep the second link, keep the first link in this fixed position and have the second link rotate at constant speed, positive speed. Do we need force and torques to execute this type of motion? It's a very particular motion. Well, let's look at the equation. Plug in on the left-hand side those values and look at the resulting u. Well, if we do this, we end up with a u which has this form, 0 minus m2 dc2 cosine of alpha t. Okay? So, comment. In order to let this link rotate at constant speed, we don't need to apply any torque. Because initially it has a speed, there's no dissipation, so there's no friction. So it's like a mass moving at uniform constant speed in a frictionless environment. This is the rotational part. The link can rotate without the need of applying torque because it will keep its uniform constant velocity without the need of an extra torque, because there is no dissipative term considered. If there were friction, of course, I need to apply a torque that compensates for this friction so that the velocity keeps at the same speed. But the nice thing is this second torque. This is a sinusoidal torque, or cosinusoidal, it's the same, that needs to be applied on link 1 in order not to move link 1 because of the effect of the rotation of link 2. So this is exactly the torque that needs to be applied by the motor at link 1 so that we can see this link rotating without the prismatic joint being moved. And you see that it has the same angular profile of the speed here, and it has a minus sign because it contrasts the effect of the torque, of the induced torque. This is an inertial effect that needs to be compensated. Actually, sorry, it's not an inertial effect. It's the effect of compensating the centrifugal terms, the quadratic term. Sorry, no, I'm confusing now. This q dot 2 is in fact on the first joint. Okay, I think there's something missing here. There's something missing here, in fact. Sorry about that. So what I wrote is just the effect of m to the c cosine alpha t times, oh, what is missing is this, is of course, is alpha dot square. Oh, okay, now things. So there's no inertial effect. There's only a term which pulsates with the angle q2 and has the square value of this velocity. This is coming from here. So in fact, it's the couple, it's the torque or the force that we need to apply to joint 1 in such a way that the centrifugal effect is being compensated and the joint will not move because of the rotation. So this has a very nice interpretation, although I made some confusion now, but I was just missing the alpha square terms, which corresponds to q dot 2. So this is one example. Let's do a second example. The second example, in this case, we assume that the motion of q1 desired on time is a sinusoidal motion. And I will write this in this following form. Okay? Sorry, cosine of t. So that q1 desired of 0 for time 0, cosine is 1, so this will start from 0. And associated to this, by differentiation, q1 desired of t dot, so it will be the derivative of this, so the derivative of minus cosine omega t is omega sine of t, so we have a omega sine omega t, which means that initially the velocity of joint 1 is 0. And finally, q1 double dot of t is the derivative of this, so a omega square cosine of omega t. And this will imply that at time 0, the acceleration, since this is 1, will be equal to a omega square. Okay, so different from 0. While the second link will be, should be kept at the constant value, pi over 2, which means that q2 dot and q double dot will be equal to 0. Okay, so how is the situation? Let me draw a picture here. We have the first joint, which is prismatic, and then we have the second link placed at pi over 2, okay, and this distance is q1, so initially q1 is 0, it means that we are here, and then we have to execute this periodic motion. So this will move the first link here and then go back and then go back. So if we draw over time what happens to q1 desired, we will have a profile like this, where this is the peak of 2 times a. Okay? So this is the peak of this value. Of course, this is reached when cosine of omega t is equal to -1, so you have twice a. So this peak is reached when we have p over omega as time. So we are moving up and down the first joint while trying to keep this always at equilibrium. You can imagine if I accelerate this link will tend to fall in this direction. If I accelerate this in the other direction, this will tend to fall in the other direction. So we need to apply some torque to keep this type of equilibrium. And in fact, the desired torque, in this case, as a function of time, will be m1 plus m2 a omega square times cosine of omega t, and the second will be minus m2 dc2 times a omega square cosine of omega t. And this computation follows from replacing on the left-hand side all the desired value and their derivative and having this evaluation. So the result is the following. In order to have a periodic motion of the first link up and down, so going here and then going back and then again, you need to apply a torque which has the same sign of the acceleration. This is positive, everything is positive and has the same sign of the acceleration. You see cosine and cosine goes together. So this is natural. No? I'm moving up and down, so when I accelerate here, I have to apply a force in this direction and vice versa. However, in order to keep this in equilibrium and not to let him rotate because of the coupling with the first joint, we need a torque which has the same profile of this, but if you compute all these things, these are all positive with a minus sign. So it's going opposite to the force that you're applying here or to the acceleration. So when you accelerate like this will tend to fall. So you accelerate positively, this will tend to fall in this direction. So in the counterclockwise, and you need to apply a torque in the clockwise direction, so with the minus sign. Remember, the positive sign is counterclockwise. And vice versa, if you're accelerating in this direction, so with a negative acceleration, this will tend to fall here. You need to apply a clockwise torque by this minus. So minus and minus acceleration, it will be a positive torque. Okay, so you see that this type of analysis is instructive. Of course, you will not do in general such details, but just to understand, to have a familiarity on how to use the model in direct or inverse dynamics. Let me conclude this part with a Matlab computation. So here on the slide, you see a program. I distributed this to the students that are attending this course here at Sapienza. So it's a simple code which uses the symbolic toolbox of Matlab in order to derive the model of this PR robot, exactly what we have done so far in an automatic way, and just to make a slight difference, but considering that the PR robot is now in a vertical plane. So we include also potential energy. So we need to define first some symbolic terms. In fact, here, this seems instruction says that these are all symbolic labels. We define this label as real because otherwise the system will imagine that it could be complex and the computation may introduce some imaginary parts which are unnecessary. So we have the mass of the first link, the mass of the second link. I call D just the distance from the center of mass of the second link to the joint axis. And then we have some inertia, three components of the diagonal inertia matrix of the second link. Of course, only the last component will contribute. And then we define a symbolic variable, also Q1 and Q2, and the derivative Q1 dot and Q2 dot, which I call dQ1 and dQ2, and the acceleration as well. U1 and U2 are the non-conservative forces and generalized forces at the two joints. G0 is the acceleration of gravity. And also these are real. Now, when you go through, you start by computing the kinetic energy of the first link. Let me see. Okay. The kinetic energy of the first link, which is very simple. Then we do the computation of the position of the center of mass of the second link, the velocity, and then the contribution of the linear part, so the velocity of the center mass to the kinetic energy, and then the contribution of the angular part, and then the total kinetic energy will be the sum of the two. So at this point, we will compute the total kinetic energy, and then we will make some simplification. We use the simplify collect instruction of the symbolic toolbox in order to make, let's say, trigonometric simplification. Otherwise, you will tend to have longer expression. From there, we extract the robot inertia matrix, and this is quite important. How do we do this? We extract the element 1, 1 from the total kinetic energy by doing twice the derivative with respect to Q1 dot, because this will be the factor multiplying the square of the velocity of joint 1. Same thing for the second one. Pay attention. The factor 1/2 will disappear automatically in this differentiation, so you don't have to care for that. And for the off-diagonal term, so you're taking first the derivative with respect to Q1 dot, and then of this temporary quantity with respect to Q2 dot. In this case, you will still have a factor 2, but this will be distributed among the two off-diagonal term of the inertia. So this is the right way of doing computation. You can apply a simplification at the end, and from there on, you compute the Christoffel matrices. So you consider the first column of the matrix M. This is the Matlab notation. So you have M1 taking all the elements of the first column, so with the index 1 in the second position, then all the elements of the second column, and then you apply this instruction, which is exactly doing the computation with the Christoffel symbol. The Jacobian instruction in Matlab is making the partial derivative of a vector with respect to another vector, while the differentiation function makes the differentiation of whatever variable you have here, a scalar, a vector, or a matrix, like in this case, with respect to a single variable. This is why one is Jacobian and one is differential. So once you have this, then you build up the centrifugal and Coriolis term. You don't have Coriolis term here. And what is new here is that you compute next here the potential term. So you put to 0 the potential error of the first link, because when this moves, it doesn't change height with respect to the gravity field, so the potential will be constant. I set equal to 0. I could have set any arbitrary value, because then in the gradient this will disappear. While in the second case, I'm using the general formulas minus the mass of link 2 times the scalar product between the gravity acceleration vector and the position of the center of mass of link 2. And then you add up these things and you make the Jacobian of u, which is the partial derivative of u with respect to the q, and this will generate the g vector. Okay, and then you can organize everything together. Now let's run this program, I hope. Oh. Something happened. Okay. Let's do it again. Okay. So let's run this and open the window like this. Okay, so there are many poses so that we can see the various terms. So dynamic model of the Pierre planar robot in a vertical plane. Okay, I have to put myself here. Okay, now it should go. Okay, so this is the kinetic energy of link 1. And you see it's a compact notation, 1/2 of m1 times q1 dot, so dq1 square. This is all we need for computing the linear part of the kinetic energy of link 2. So we first characterize its position in the 3D space. Then we take the derivative with respect to time, which means that we take the partial derivative with respect to q, and we introduce for each derivative its associated velocity. And then we compute the linear velocity of the center of mass. And then we introduce the angular velocity of the second link. Indeed, this is a planar motion, no matter if in the vertical plane or in the horizontal plane. So the angular velocity will be orthogonal to the plane of motion, so along the z-axis with a speed q dot 2. And the angular contribution will be the following. And if we put everything together, we have this long expression. Now, this long expression can be simplified. In fact, in the code, as I showed, we introduce a simplify and collect instruction. And in fact, if you do this, you just recognize that the expression slightly reduced in length because the system is able to make some simplification and reconstruction of collecting terms. So now we have the total kinetic energy, a quadratic terms in q1 dot, a quadratic terms in q2 dot, and a term in the cross product. So this we'll extract from this information, from this scalar, the elements of the inertia matrix. And in fact, the robotic inertia matrix is exactly what we found in the slide. So m1 plus m2, and then you have this off-diagonal terms that couples inertially the first joint to the second one, and then a constant term in position 2, 2. Now from this, we compute the Christoffel symbol, so we do the computation using the columns of M and the total matrix, and we do partial derivative properly organized with respect to the Q's variable. And so we have the Christoffel matrices. This is the first matrix, which should be introduced in the quadratic form in the velocity. You see that there's only one diagonal term below, so this will only give a contribution in terms of Q dot 2 square, as we have seen. The second matrix is identically 0. This is the simplification that we've done before. So that the centrifugal vector has only a contribution of the centrifugal term in the first joint and none on the second one. Now, potential energy of link 1, we said it's constant. We can set this constant to 0. The potential energy of link 2 takes this expression. This is nothing else than the height related to the height of the center of mass with respect to the gravitational field. The more high is the center of mass, the more potential has the system. Then we compute the total kinetic energy is given only by this, and we make the gradient of this term. This term does not depend in this case on Q1. Pay attention. In general, it depends. It's only because the Q1 moves the first link horizontally, so it doesn't change the potential energy. So there's only a function of Q2 when we take the gradient. The derivative with respect to Q1 is 0. The second terms in the vector G is non-zero and gives rise to the gravity term. So if we put everything together, this is a trick in which I could introduce the expression equal to U1 and U2 at the end. And here you recognize the quadratic terms in the velocity, one element in the inertial terms multiplying the first acceleration, the second element multiplying the second acceleration. In the second equation, you have an extra contribution to gravity, while the other two terms are weighting the first and second acceleration. There is no terms in the quadratic velocity because we have seen that there's no centrifugal nor Coriolis terms on the second equation. And this is exactly the same result that we had. The additional term because of gravity is only this. This is also instructive in the sense that if you have a system with gravity or without gravity, one part of the computation are exactly the same. So you add only what you were missing in one case, so the presence of gravity. All the rest of the computation have already been done, and this is the result of this outcome. So I think that we can stop here for today. Thank you for listening.